Okay, perfect. Then let's get started right away. I hope you can hear me well. If not, please let me know in the chat. So I'm going to be presenting you a preprint that we published a couple of weeks ago that we're going to present at a conference later this year, which has the topic Tensor Program Optimization for the RISC-V vector extension using probabilistic programs. I can say some words about myself. I'm a PhD student at the University of Tübingen under the supervision of Professor Oliver Ringmann, and I'm also working as a researcher at the Forschungszentrum Informatik in Karlsruhe, which loosely translated to English would be a Research Center for Information Technology. So I think I'm going to start directly with the presentation. I hope you can see my screen. And yes, good. So this project was developed during the Green Edge project, which is funded by the German Federal Ministry of Research, Technology and Space. The main idea of the project is to investigate green ways, so environmentally friendly, power-saving solutions for the monitoring of traffic, for traffic intersections. You can access the preprint here. Yes, so let's get started right away. Only a couple of words about the FZI and who we are. So we were founded 40 years ago as a research center and transfer institution in the field of computer science, and we are innovation partners of the Karlsruhe Institute of Technology. Our main building is in Karlsruhe in Germany, and we have approximately around 250 researchers working at our institute, and we focus on all these different application areas that you can see here. So from production healthcare, information and communication technology, we have a very strong group in mobility, transportation and logistics also, buildings and public spaces, and so on. Now for my presentation, I'm going to start with a motivation. Why do we need this kind of tensor program optimization for the vector instruction extension of RISC-V? Then I'm going to give a very long background. Sorry for that, but I really need to explain a lot of things in order to get to our proposal and how do we model the integration of the vector extension into the TBM, deep learning framework. And then I will show you the evaluation and how we compared the programs found by our solution against other proposals. So first, for the motivation. We need AI on edge devices. Of course, everyone wants to have different kinds of artificial intelligence algorithms on edge devices. This could be a mobile phone, but this could be something else. This could be a smart camera. This could be anything that you can imagine. But of course, these devices come with latency constraints, power constraints, and memory limitations. So it's not that straightforward to take one AI algorithm and then deploy it on an edge device. Of course, RISC-V is an excellent candidate for designing hardware to efficiently execute these AI models. So assuming that the public of this presentation already knows about RISC-V, so I'm not going to explain in detail the ISA, but of course it has an open source license. It has a very flexible instruction set architecture that can be adapted to the requirements of the specific applications, which makes it a very good candidate. And it already has suitable extensions for the ISA for the execution of the mathematical operations that AI models require. For example, the vector extension, which will be the focus of this presentation. But of course, hardware is not enough. So we can have a very good hardware, a very tailored hardware for our specific application, but we also need the software to map the mathematical operations of the AI model onto this hardware. And this is where we come in. We need some kind of software that is flexible so that, people that train AI algorithms, they use a lot of different frameworks. So we need to have some kind of deployment tool flow, deployment workflow that supports the input of these models from different frameworks. We need to integrate different hardware backends because sometimes you will want to deploy on a CPU with custom extensions or on a CPU with standard extensions like the vector extension. Sometimes you would want to deploy your algorithm on a CPU that is attached to a custom accelerator, so you will have to generate other kinds of instructions. And we would like to have design space exploration capabilities. So it's not enough to say we map this convolution operation, this matrix multiplication operation in this manner onto the hardware, but we also want to explore different ways to map this mathematical operation. And I'm going to talk a little bit more about it during the background section. So now I'm going to focus on a very brief explanation of the RISC-V vector extension. Then I'm going to give an introduction to TVM, and then the MetaSchedule framework, which is where we integrated the vector extension from RISC-V. So for the vector extension of RISC-V, it has a number of features, which the most important for this presentation are it has 32 vector registers, each up to VLN bits wide. So this is once the CPU is constructed, this is fixed. But then we have some programmable parameters that can be selected during the runtime. So one is the selected element width, so the actual width in bits of each element in the vector that is going to be processed. LMUL, which is a group multiplier, which allows to group multiple vector registers and do a vector operation on more than what fits inside only one vector register. And then we have VL, which is the actual amount of elements that is going to be processed by one vector instruction. Of these three parameters, we get one parameter that is very important, which is VL max. So this is the maximum amount of elements that can be processed by a vector instruction, given the configurations that the programmer chose, LMUL and the selected element width. Of course, the full specification, vector specification, is much, much, much bigger. So if you are interested, I will leave you there a link. But in order to show a little bit how these parameters change, how the vector instructions behave, we have this figure on the right. So in this example here, for example, we have two vector registers, each one with a length of 64 bits. And in the first case, for example, maybe let's take a look at the second case, which is more interesting. I don't know if you can see my pointer, but I'm pointing at the second example. We have VL max would be 8 because we are selecting an LMUL, so a group multiplier of 2. So we are grouping two vector registers. We are selecting an element width of 16. For example, maybe we are doing vector multiplications with int 16 data types. And because maybe our mathematical operation that we are trying to do only has 6 elements, so we are selecting that we're going to operate on 6 elements with VL. So this is a little bit to exemplify how the selection of these parameters modifies how many registers are used and how many elements of these registers are used. So how do you use these vector instructions actually in practice? So for example, LLVM and GCC already provide intrinsics if the user wants to write its own kernels using these instructions. So I'm giving here an example of the GCC on the top, how it looks like, and of LLVM on the bottom. As you can see, for example, on the top for the GCC intrinsic, we have the actual vector instruction here marked in green, but we have, for example, the output vector data type here on the left, the data types of the input vectors on here on red, the actual amount of elements that are going to be processed in these variables, and so on. The same similar happens with the LLVM intrinsics. This is interesting, of course, but these compilers, both GCC and LLVM, also apply some kind of autovectorization. So they will automatically, from the code, generate the vector instructions accordingly. So the user does not have to write its own for loops and everything, calculating the, for example, the matrix multiplication using vector instructions. Good. Now let's take a look at what TVM is. Maybe some in the public are already familiar with TVM, but as a general, very high-level overview of what TVM is, TVM is a deep learning compiler. So you can insert into the framework AI models trained on mostly any framework that there is available, although the most used are PyTorch and maybe TensorFlow Lite or ONNX, for example. Then it represents this network using an internal representation. It has two levels. So one level is the more high-level representation, which has full layers. For example, this is a convolution that is followed by a fully connected layer, and there is maybe a concatenation layer and this kind of stuff. Previously, it was called Relay. Now the new versions of TVM has a new intermediate representation for this that is called Relax, which is more flexible. And then we have the Tensor AR, which is the TIR, and I'm going to be referring to this during the presentation, so keep it in mind. So this is the intermediate representation that really explains how the actual mathematical operation is executed. So here we have the actual for loops and the actual vectorization or hardware capabilities into this IR. And I'm going to show you later how it looks like. And then TVM provides code gens to target different backends. For example, TVM can generate C code directly from this neural network. And then there are runtimes to execute this C code, for example, on a CPU. Or you can generate, for example, LLVM IR, and then execute this IR using the TVM runtime if you have a Linux compatible computer or edge device where you can compile the TVM runtime. One of the most important parts of TVM, and it's the part that is also important for this presentation, is the automatic optimization of the Tensor AR. So the Tensor AR, as I said, is a representation of the mathematical operation that the layer of the AI model has to do. And we can map this in different ways. And this can be found, so the best way of mapping this mathematical operation onto the selected hardware can be done using this MetaSchedule framework. We are going to talk more about it later, so I'm not going to mention this anymore. But this is very important, and I know I think Philip is also here in the presentation. So if you have any questions about this, please refer to him. There is already an existing workflow using TVM to deploy AI models on RISC-V CPUs that have the vector extension. But this only supports, for now, int8 models, so quantized AI models, and it doesn't support the automatic optimization features of TVM. So basically what it does is it uses the CMSIS NN target of TVM to generate C code, And then Moore RISC-V NN provides handcrafted implementations of the different layers. For example, how a convolution should be executed, how a fully connected layer should be executed. And these are already written by someone from the guys that developed the library. And these are used to execute the mathematical operation on the vector extension. But because these are handcrafted and are already written, so they don't have the flexibility to support this automatic optimization. Cool. I'm going to compare our work against Moore RISC-V later during the evaluation section. That's why I'm mentioning it right now. So let's go to the MetaSchedule framework. So now we are talking about this part of the framework that optimizes the execution of the specific Tensor AR functions onto the selected hardware. So it starts with an AI workload. As I said, this is a very high-level representation. So you have the sequence of layers in your AI workload. Then from here, each Tensor AR program is extracted. So you can see how already this here looks very different to just saying this is a dense layer, so a matrix multiplication for easy understanding. So here we have the actual loops and the actual multiplication with accumulation that we need to do. And then what MetaSchedule does is it generates a search space of possible transformations for these Tensor AR programs. And this is done automatically by the framework using some features that I'm going to present next. But the most important thing to keep in mind here is that the search space generates a lot of different candidates. And these candidates are generated applying transformations, for example, loop tiling, loop reordering, or even hardware acceleration. So replacing some of these loops with a specific hardware instruction that executes these loops is, for example, one of the features that could appear inside these candidates. So now we have a huge search space of candidates, and we would like to find the best one. And for that, TVM already provides this automatic optimization framework where if you have the hardware connected to the host machine where you are compiling your neural network or your AI workload in general, then it takes a candidate, it measures the candidate on the hardware, and then it reads how fast this candidate was, so the latency of this specific candidate. It puts it into a search algorithm that then will select the next candidate to try, and the loop continues. And this continues until a fixed amount of iterations is reached. This can be selected by the user. And in the end, the optimized Tensor program is exported. So the idea of all this is to find, as I said, the best candidate for the for each one of the Tensor AR programs that were extracted from the initial AI workload. Now, this is a very good example that I extracted from the original paper on MetaSchedule, which I wanted to show you very quickly. This is how MetaSchedule generates the search space. And I'm explaining this because this is exactly where we inserted our modifications for the specific deployment on the vector extension of RISC-V. So MetaSchedule is built around this probabilistic program feature. The idea is that you can sample different random tiles for a specific loop, and then you can apply these sampled tiles, for example, to a loop to tile it. And this is just the definition of your probabilistic program. But then, during the generation of the search space, you get the actual schedule, the actual modified program based on this probabilistic program that you wrote first. And the best way to see it is with an example. So this would be the initial Tensor IR program, and then in the first step, the first sample tile is applied, so a tile is sampled, and then for example, the I loop is split into 2 loops, and this is what it's represented here. So these 2 parameters here, how this was sampled, how this loop was splitted, this was selected by this sample tile in a random manner. And then we apply the next probabilistic program section, which would be, okay, where are we going to execute this ReLU function? And this is also sampled randomly from the different possible locations where you could execute your function. And you can get, for example, 2 different programs here, because the sample compute location can give you 2 different outputs. So in this way, by sampling different parameters that are then used for the actual transformations of the Tensor AR, you get different candidates. So this is very quickly how MetaSchedule works inside. The main idea to take from this slide is that in order to build the search space, there are parameters to modify the loops and the transformations that are applied that are sampled randomly. And a very good example is, for example, this function here, which is exactly the function that we are going to use later to explain our proposal. So there is a function in the MetaSchedule that is called multi-level tiling within Trin. And the idea is that you provide this function with an intrinsic definition and an intrinsic implementation. So the main idea here is you have some hardware that can do this mathematical operation here in the definition, and you have the implementation. So how the hardware actually does this mathematical operation, with which instructions. And you have an initial Tensor AR program, and you want to transform this Tensor AR program in some way automatically, so that you can insert this intrinsic implementation into the Tensor AR program. And this works in 2 steps. So the first step is transforming and tiling the Tensor AR program using the definition. So using the definition, MetaSchedule automatically knows, okay, the inner loops need to be size 4, for example, and it applies the tiling accordingly. And then we get a tiled program that is a little bit more complicated, but you can see here that we have, this looks more or less like the intrinsic definition here on the top. And now the second step is to actually replace this, considering all the buffer dependencies and so on. But the main idea is to replace this with the intrinsic implementation. This is just, of course, a generic intrinsic implementation. Now we're going to go at what we exactly integrated here. And in the end, you get a Tensor program with hardware-specific implementations. So we went from a Tensor AR program that is very generic to a Tensor AR program that utilizes the specific instructions from our hardware using this function from MetaSchedule. And this already exists in TVM for Intel, for ARM CPUs, for example, for NVIDIA GPUs, but until now, RISC-V has been missing. And what we did was specifically add the intrinsics in order for MetaSchedule to be able to map this onto the vector instruction. So let's go directly to the proposal now. What are the challenges by integrating this into the MetaSchedule framework? Most of the challenges come from the flexibility of the RISC-V vector extension, because the programmer can select during runtime these parameters like the vector grouping, the selected element width, and the actual amount of elements that are going to be processed by each vector instruction. And these we need to, in some way, support in our integration. So let's see how we did that. And also, the other challenge is, I mentioned there is already one way of deploying AI workloads onto the vector instruction set extension, but this only works now for int8, and we wanted to extend it for floating point 16, floating point 32. So why is this a challenge? So for example, let's say we define an intrinsic implementation that multiplies a 4-element vector with a 4x4 matrix. We are already limiting ourselves. So this is not good. Because if we define this in our compiler as our intrinsic, then later, if we are trying to deploy an AI model on a different RISC-V CPU that has a different vector length, then we are not using the vector unit as much as we could, because, for example, VLMax could be much, much bigger than 4, and we are not using it. So we need to define stuff in some way that is dynamic and that we can, during the compilation of the AI model, modify to adapt to the actual hardware values, hardware parameters of the RISC-V CPU to which we are trying to compile the model, for which we are trying to compile the model. And this is how the definition looks like. So I'm not going to explain everything here. I'm just going to mention 2 things quickly. So as you can see, the input for the definition, so what I showed before in a more pseudocode kind of way, this is how you actually define it in Python. And here you can see there is no specific information about RISC-V. There is just a definition of, I want to deploy this mathematical operation, and then I'm going to provide an implementation of how to deploy it. But what you can see here interesting is that the vector length, for example, for this operation that we are trying to deploy here is a variable. So it's not constant anymore. So during runtime, during the compilation of the neural network, we can use this to select and increase the search space with different definitions. That we are going to come to that in a moment. And also the data types are also configurable during the compilation of the neural network. I'm not going to show you how the actual implementation looks like, because that's very long and it's much more complicated. But just as a very reduced way of explaining it, we provide 2 intrinsics. So this is the first intrinsic, its definition on the left, its implementation on the right. And in a very abstract manner, what we are trying to do here is use the vector multiply and accumulate instruction from RISC-V to do vector-vector element-wise multiplication with accumulation. So you can see that the actual intrinsic, the actual implementation looks very simple, but its integration into the MetaSchedule framework is what allows us to later find very optimized programs based on this tuning process that we do later. Yes, one important aspect that I want to highlight here is because the implementation is also written in Python, we can target both GCC intrinsics and LLVM intrinsics. So during the compilation of the AI model, if we find that we are trying to compile targeting, configuring TVM to generate C code, then we can, inside the implementation, generate the GCC intrinsics, like this that we are seeing here. So we can very easily in Python, using some string interpolation and so on, select the specific instruction that we would try to use, and select the output vector data types, input vector data types, VL, and so on. So this will be one of the intrinsics. The other intrinsic is a little bit more complicated, but it's basically a vector matrix multiplication. Again, I'm not going to show exactly the implementation code because it's fairly long, but in a very general manner, this is how it looks like. So we load the vector onto a vector register, and then we reuse these vector register values multiple times. and we multiply every time with a different row of the matrix that we are multiplying with, and we are accumulating with the previous value of the C matrix here. So it's a mostly standard vector matrix operation. What is important here is this reuse factor, this J, that we selected empirically to be VLEN divided by 32, because the biggest data type that we are supporting is 32 bits. Again, this is just the pseudocode of the implementation, but in the actual implementation described in Python, we are replacing this, for example, vmul with the exact intrinsic that we need based on the parameters that we defined here with the VL and the input data types and the output data types. So everything is configurable. And how does this integrate into the search-based generation of MetaSchedule? Because that's exactly where we want to integrate this. As I said, our definitions are parameterizable, so you can configure them by data type and vector size. And while generating the search space, we use this function that I explained later, this multi-level tiling within Trin, to transform the Tensor programs and insert our implementations into these Tensor programs. So basically, this looks a little bit like this. During the search space generation, so remember, this is before we measure each candidate on the hardware. So we are first generating the entire search space of different candidates that we are trying to measure on our hardware. And one of those candidates would be the best optimized way of executing that mathematical operation. So it's not a global optimum, but it's probably a local optimum. So we get a Tensor AR workload that describes, for example, a matrix multiplication. And for each data type, so we support int 8, float 16, and float 32. For each data type, we select the VL max accordingly. How do we get this? Because when you configure TVM, you give him the target. So what are you trying to compile for? And this is how it looks like. Very, very reduced version, because actually both have more parameters, but I'm trying to keep this small just for the things that are important for the slide. But for example, this is how you define the C target. And you can provide in the mark parameter, you can provide the length of a vector register. So we can extract this information from here and use it to calculate VL max based on also the data type that you're trying to accelerate. And then we call multi-level, then we configure our definition. So this definition here, we configure with the data type that we are trying to use to transform this Tensor IR, and we configure the VL, and we apply the multi-level tiling within Trin. And this gets us one candidate. And then we reduce VL a lot of times until we arrive at 4. We have found empirically that when VL is less than 4, then it doesn't really make sense to use vector instructions. And we do this for each data type. So what does this mean for the search-based generation? In the end, because we are modifying the same TIR workload, so the Tensor IR workload, with different values of VL and different configurations of our intrinsics definitions, we obtain in the end candidates that are trying out different values of VL, for example. So one candidate will try to execute the matrix multiplication doing vector-vector operations with, for example, 32 elements, and another one will try out with 16 elements. But because the other parts of the Tensor IR program, so also, for example, the loop tiling of the other loops is also being changed by the MetaSchedule, this gets us a lot of different candidates that are using the vector instructions, because we defined it so in our implementation, for the very small part that we defined that we can accelerate with the vector extension. I hope that was clear. So basically what we are getting here is a lot of candidates that are using the vector intrinsics that we defined. That's the key message here. So we evaluated this to verify if it really is able to find better programs that are faster than other approaches. And what we evaluated two different targets, let's say. First, we implemented on an FPGA a Rocket Core CPU attached to a Saturn vector unit. This is a vector unit from that was published last year, and that can be very easily attached with the Rocket Core CPU using, for example, the Chipyard repository. And because we are implementing on an FPGA, we can try different VLANs. So we can actually implement a vector unit with 256, 512, 1024 bits, and then evaluate how do the programs that execute on these different vector units are modified by this vector length. And in order to execute the generated code, so the output of TVM, in order to execute it onto this CPU with this vector unit, we are using the micro TVM runtime. So this is a reduced runtime from TVM written in C and C++. And we are compiling it together with the Sapphire RTOS to communicate with the computer and so on. And all of this is compiled with GCC 14, just as a reference. And on the other side, we're using a commercial board. So the Banana Pi F3 is a commercial board that has a RISC-V CPU inside. If I don't remember it correctly, it's 8 cores. And of course, because it's a commercial board, it has already a fixed VLAN of 256 bits. So this we cannot change. But it's still interesting to deploy these AI workloads on this commercial board and see if we are also able to find better networks that are run faster than the standard way of doing it, which will be compile with TVM using the LLVM backend and then run it on the TVM runtime. Because this is a commercial board that is more powerful than the Rocket Core that is running on the FPGA, here we can run, for example, a Linux distro. And we run on different amounts of workloads. So we tune matrix multiplications with different sizes. So here we have square matrix multiplications, but this is totally generic. So the actual workflow and the actual methodology can be used for any size of matrix multiplication. We tuned different convolutional neural networks. So we extracted convolutional neural networks from the MLPerf Tiny benchmark, MobileNet version 2, ResNet 18. We have transformers for NLP tasks like BERT, generative adversarial networks examples like DCGAN, and even, of course, some of these models do not fit on the FPGA-based design or are very, very slow on the FPGA-based design, even with the 1024 bit length vector unit. So, for example, the large language model that we tried here, which is mobile LLM, which is a very small LLM, but still able to give meaningful results. This we only tuned on the commercial board, on the Banana Pi. But this a little bit gives us a selection of different workloads that all of them have different layers, and each layer needs to be tuned by our MetaSchedule process with our intrinsics. And in the end, we evaluate the performance of the entire network, and we see how it compares with other approaches. So basically, for the matrix multiplication results measured on the Saturn vector unit with VLAN 1024, here we are comparing the non-tuned version. So this is the C code generated by TVM, compiled with GCC, as I said, but without any optimization. So without any optimization, using the -OS flag, so for optimizing for size. But this does not use any vector instructions. Then we are comparing exactly the same code, but compiled with a -03 flag. So in this case, we get code that actually uses some vector instructions automatically decided by GCC. And then we compared against RISC-V NN, which I mentioned earlier. But we can only compare using int8 quantized networks, because for the other data types, RISC-V NN does not support these networks as input. And as we can see here, ours would be the yellow one. And we see on the top latency and on the bottom speed up compared with the non-tuned version, which maybe it's easier to compare only the speed up. We can see that our results are able to find faster schedules than all the other options. Which schedule, I mean a candidate for a Tensor AR program. So for these specific matrix multiplications with dimensions 16, 32, 64, etc., our solution, so using MetaSchedule combined with our intrinsics definitions, are able to accelerate, to find better candidates to accelerate these matrix multiplications. And we are not showing it here, but the results for the other VLANs also follow the same pattern. So we are able to find always better solutions than just applying the autovectorization feature of GCC, and also using RISC-V NN for the int8 networks. Now, what we also did was, okay, we analyzed the instruction traces executing RISC-V NN workloads versus our schedule. So for the int8 matrix multiplications, we looked at the instruction traces, executing them on QEMU, and we extracted this information, which, for example, the first step is our proposal has much smaller code size than RISC-V NN. So this is because our proposal finds specific candidates for each matrix multiplication, and it has less. This is what I think it has less. Let's say boilerplate code. And so this would be the orange line here. So for the different matrix multiplications, it's always around 80% of reduction in code size. Our proposal executes less amount of vector instructions than RISC-V NN. So maybe this explains a little bit why it's faster. So it executes the same operation, but uses less vector instructions. And if you take a look only at the vector instructions and see the different groups of vector instructions, we can see it's almost impossible to see because it's so little, but our proposal uses much less amount of store, the vector store instructions. So maybe this is also a reason why our candidates found by our MetaSchedule plus our intrinsic definitions solution are faster than the ones provided by RISC-V. Yes, so then we tuned complete workloads. So as I said, convolutional neural networks and other ones. The names are a little bit small here, but the results are the same as before. So basically, using GCC autovectorization flag is better than just using the non-tuned, let's say, the output of TVM as it is. But using RISC-V NN is even better, as you can see here in the orange ones. But in the end, okay, I just saw there is an error here. Please excuse me. Float 16, float 32. The orange bars here should be yellow. So RISC-V doesn't support float 16, float 32. So it doesn't make sense that this is orange here. Sorry for that. Yes. So in these cases, this should be yellow, but you can see that all the yellow bars, if you replace the float 16 and float 32, are always smaller in latency and better in speed up or improvement in the bottom graphs. So the candidates found by our solution end up resulting in networks that run faster on the same hardware. We took a look at the same again with the instruction traces, and we found the same except for one network, which was the anomaly detection network. We can maybe explain this because the anomaly detection network has all layers that are all exactly the same with the same parameters, and it seems that the implementation for that specific type of layer is more efficient, or at least is smaller in code size than ours in RISC-V. So this is the only one in which our code is better. So the code size reduction is negative because our code is bigger than the one generated by RISC-V. Also, our solution still executes less amount of store instructions than RISC-V. So maybe that's also a reason why it's faster. Although we can see on the top graph that our solution in this case for complete networks, so these are convolutional neural networks, so there are more amount of convolutional layers. It seems that for convolutional layers, our solution executes more vector instructions, but much less amount of other instructions. So it seems that our solution is utilizing the vector unit much more efficiently. And then very quickly, I want to show you the results for the Banana Pi, so for this commercial board. And here we did not compare RISC-V because the workflow for RISC-V was for the C code target for TVM, and here we are trying to compile with the LLVM target to use the LLVM intrinsics. But here we compare the non-tuned version, so this would be the LLVM target, but without enabling the vector extension. So as you can see here, this would be, for example, the LLVM target for TVM. And for the non-tuned version, we don't give it the attributes V and VLEN. And then we have the non-tuned with vector enabled. So this would be this target here, which would be the blue bars on the bottom. And then we have the orange, which is ours. And you can see here that, again, for int8 workloads, it seems LLVM is pretty good at generating candidates, generating schedules without any tuning. So out of the box, it already provides a lot of improvement. But still, using our proposals, the matrix multiplications run faster. So this is also a good results for us. And if we take a look at complete networks, and we take a look at how this behaves, there is only one or two examples, I think, here. For example, here, image classification for floating point 16 and floating point 32, where the autovectorization of LLVM was able to find networks that were executed faster than the ones found by our solution. And this is a limitation. This would be the only place where our workflow failed to find better networks, better candidates. But this could be improved by running the MetaSchedule process longer. So generating more candidates and trying out more candidates. But we can see that as a conclusion for all the other workloads, the candidates found by our solution end up being faster than the ones provided by LLVM with autovectorization and without autovectorization. So as a conclusion, we presented how to modify the MetaSchedule framework to enable the tuning of AI workloads on RISC-V CPUs that support the vector extension. We tuned these different AI workloads on SoCs that have different vector unit parameters. This we evaluated on an FPGA. And then we compared it with RISC-V, which is a previous work. It was the previous way of deploying these workloads on RISC-V CPUs with vector instruction. And we compared it with the autovectorization feature of GCC 14. We then analyze instruction traces, and we try to justify why our schedules why our candidates are faster than the ones provided by RISC-V NN. And then we did the same, evaluating on a commercially available board, and compared the programs, and we found our programs are also better than the ones that are provided by LLVM19, by the autovectorization feature of LLVM19. There is one thing pending for this work, which would be the open sourcing of our extension to TVM. So this is already ready, but we are missing some internal approvals to achieve this. But I'm confident that in the next weeks, we are going to generate the merge request for this feature into TVM. And there is one disadvantage that is very important to mention. So MetaSchedule, as I said, is an iterative process that requires measurement of candidates on the real hardware. So each candidate needs to be compiled, needs to be flashed onto the hardware where we are trying to measure it, needs to be measured, and then the search algorithm needs to select the next candidate, and so on and so forth. So this takes time, of course. So this is why solutions like using the autovectorization or using RISC-V NN are still good options when trying to do very quick prototyping. But as we could see, if we would try to extract every minimum ounce of performance of your hardware, it makes sense to execute this MetaSchedule process, this iterative search process, because you end up with faster mappings that make your AI workloads faster, basically. So thank you very much for your attention. I know we are almost ready with time, but I hope we have time for some questions.
Can you hear me now?
Yes.
Oh, finally. So sorry for that issue at the beginning. So thank you very much, Frederico, for your presentation. So I missed your introduction, but I'm going to ensure that we put that when we do the editing of the recording. So folks, if you have any questions and you want to ask that verbally, just raise your hand and we can allow you to talk. Otherwise, you can paste your question in the chat. So we have a couple of questions in the chat. Maybe you can go through them and see what need to be answered.
Yes, I saw the question about LMUL, which is something I didn't have time to explain here during the presentation. We fixed LMUL in our case to use to group as many vector registers as possible, given the other parameters. So given the parameter of the actual element width that we are trying to deploy with our intrinsic, and giving the VL that we are trying to deploy, then we fixed LMUL for using as many vector registers as possible. This was a design decision, but yes, it is possible to also use these to explore different values of LMUL. It's definitely possible. It's definitely something where I want to go next, but it will require to modify a little bit the search-based generation. So basically, it would mean adding one more parameter into the definition and into the implementation. So making the implementation more flexible so that it also configures itself based on the LMUL that you get from outside. And then during the search space generation, generating different candidates based on different values of LMUL. But this is definitely something possible, yes.
There's a question about, did you have to transform the data kernel layout to make sure that the Tensor intrinsics actually have a compatible memory access pattern?
Actually, no, this was not needed. This was, I know what you mean. Sorry, I know what you mean. Yes, you're right. For example, for convolutions, we had to change the layout of the weight matrices so that they have a very specific layout with channel last. It was so input channels last, I think it was. But this is automatically also done by TVM, so it's fairly easy to implement like a pre-process pass And because the weight matrices are constant, this is all done during compilation time, and then during runtime you already get a weight matrix that is already transformed. So this doesn't add any runtime overhead during the actual execution. This just adds some compilation overhead during the search-based generation, but it's negligible compared with the actual time that is spent measuring the different candidates on the hardware.
Yeah, and I believe the last question not the last question, but one question that was not answered at the very beginning was what programming languages should one know in order to understand what you are doing. So there's
yes.
a ask.
So definitely, so if you want to take a look, once this is open source, definitely Python, because most of the integration into TVM is done in Python. But because we are generating C code basically for one part of our, for the targeting of the embedded SoCs implemented on the FPGA, of course it's good to know C. But most of the work was done in Python and C. And a little bit of C++ also to tune some stuff inside of TVM, stuff that I didn't have time to explain. But basically those are the three languages. I see there are also one question about the FPGA specs. So as a reference, it's the AMD ZCU102 board, which we used for measuring this. Yes, so it's a pretty standard old Xilinx, new AMD FPGA.
And there's a question about where to get more information about the work. So the paper
Yes.
is public available, right?
Yes, the paper is public available. There is a preprint on arXiv, so you can find it with the same name. And you can, of course, scan it right now if you want. But you can find it with the same name, or, of course, you can contact me for more information. So you have my contact information, I think, in the event data. So feel free to contact me for any question.
Okay, so it looks like we cover all the questions. Folks, are there any more questions you'd like to ask him? Yeah, looks like we do not have any. So Federico, I'd like to thank you again for presenting and for starting this with all the technical issues we had. The recording will be published in our RISC-V YouTube channel between today and tomorrow. And we're going to notify you all about the availability. So again, thank you very much for your time. Thank you for presenting. Thank you for bringing us this really interesting content, because if you look at what we're doing in RISC-V, there's a bunch of discussion about matrix and focus on AI and optimizations on that front. So feel free to join all of those task groups and participate if you're willing to. So thank you very much, Federico.
Thank you very much for the opportunity and for the space.
Thank you. Thank you everyone for joining. See you in the next RISC-V technical session. Thank you very much.
Bye-bye.